Section 12.2 is setting up what polar coordinates are and how they work. So we understand the geometry of polar coordinates now. But now we actually have to do calculus with it. So we've learned how to do a lot of stuff in calculus. Let's see what we can apply to polar coordinates. Okay, so you might think that differentiation and integration are the same processes in polar coordinates as they were in rectangular, but that is unfortunately not the case. Slope, as we define it, is the rate of change of the vertical coordinate with respect to the horizontal coordinate. So slope is still change in y over change in x. But in polar coordinates, the differentiable function r equals f of theta, it's going to have a polar form, right? So x is equal to r cosine theta, which is some function, f of theta. See, here, let me look. If r is equal to f of theta, then r is f of theta times cosine theta. And y, which is r sine of theta, is f of theta sine of theta. See? Okay, so if we put that together along with our old friend the chain rule, we can find dy dx. So dy dx is dy d theta over dx d theta, which you might think, oh, it's easy. I can just take the derivative of this with respect to theta, or this. And the answer is no, you cannot, because that's two functions multiplied. Huh? So you're going to have to use product rule and chain rule. Right? Product rule. So let's see here. Let me do the y part. So let me say that y, I want dy d theta right here. So if I'm going to take the derivative of this, I would take the derivative of f of theta, which is f prime of theta, leave the sine of theta alone, plus, then leave the f of theta alone, times the cosine theta. All right, then, and the chain rule, by the way, is this part over here. That's where chain rule's coming in. All right, so then for the x portion, let's see, here's the x portion. It would be f prime of theta times cosine of theta, right? Take the derivative of f, leave the cosine alone, plus leave the f of theta alone, and then the derivative of cosine is negative sine. Oh, negative sine. So that means that I'll have to subtract here. Right? Derivative of sine is cosine. Derivative of cosine is negative sine. This will be the slope of any polar curve's tangent line. Okay, so a couple things to note. A common mistake is for students to think they can just take the derivative of both the parts. You cannot, right? You have to use this formula. This formula is, I'm sorry to say, the formula for the slope of the tangent line. There's no avoiding it. To find the equation of the line, you would need a Cartesian point on the graph, because the equation of a line, this is point slope form. So y minus y1 equals m times x minus x1. So this is going to get you slope, right? This is going to be m. These parts, right? They're all the slope. So that right there will be your dy dx. Right, that'll get you the m part, but in order to find the rest of it, you're going to need x1 and y1, some Cartesian point. In that case, remember, x squared plus y squared equals r squared, tangent of theta is equal to y over x is equal to r cosine theta, and y is equal to r sine theta. These are things that we've just learned and know and love from 12.2. Never forget, because they will matter a lot. Also, if you're going on to Calc 3, this stuff will come up a lot in Calc 3. It will happen when you get to Cartesian, or the cylindrical and spherical coordinate systems. All right, so I have the slope of the tangent line, this thing we just derived right here, written out right here in a slightly different form because they're putting in a theta 0 implying a specific theta value. So rather than just generic, right? So saying if it's a differentiable function at this value, theta 0, then the slope of the line that's tangent to the curve, that polar curve at that point, is this. This is the slope of a tangent line, right? This is m, right? At a polar curve. Provided that the denominator is non-zero, of course, because we cannot have the denominator being 0 ever, and that continues on. At any angles theta 0 for which f of theta is equal to 0, f prime of theta is not equal to 0, and cosine of theta is not equal to 0. The tangent line is theta equals some constant with slope tangent of theta. So in other words, what they're saying is if there's an angle for which the f of thetas exist, but the f of thetas are 0, but the derivatives exist, right? They're not 0, and the cosine of theta is not 0. In other words, the denominator is not 0. Then you're going to have a diagonal line, right? This right here is a diagonal line. Through the origin, right? And it's going to have slope tangent of theta. So that's like a special case that can pop up. Other special cases, of course, right? Say if the numerator part, dy d theta, actually let me write that. So I don't like that they don't have that here. So let me just say it. So it's dy d theta over dx d theta. I'll put the m over here, right? So dy d theta, dx d theta, you can just box all of that. So if the dy d theta part is 0, then that would be a horizontal tangent line as long as the denominator is not 0 at the same time, because that would be bad. Denominator 0 is bad. If the denominator is 0, it would be a vertical tangent, right? That's what we know about. When the denominator is 0, that means your slope is undefined. That means the slope is infinite. We learned that in algebra class, right? If they're both 0 simultaneously, that would be an indeterminate form, and no conclusion can be drawn about the slope, right? So it cannot be both. If they're simultaneously 0, think about what that would mean. That would mean 0 over 0, which is an indeterminate form. We'd have to do something else. Okay, so let's look at the special cases here. So to have a horizontal tangent, so can you spot the special tangent cases? So a horizontal tangent would mean it happened kind of right up here, where the tangent line would be horizontal, right? A horizontal tangent would be right there, right? So the dy d theta at that spot, r comma theta, right? That's that point here. That point right there, r theta, would be equal to 0. Over on this side, a vertical tangent would happen right here at that point, right? And that point would be, whoop, my pen flew in my hands. So that would be r comma theta right there, right? Some point r theta. And then the derivative at that point, well, actually the dx d theta part would be equal to 0 at that point, r comma theta. That's what that vertical line means. Of course, we don't really know what these angles are. If I had to take a guess, it would look like this one has about a theta of, let's think, pi is here, pi over 2 is here. So 2 pi over 3 for that one, looks like, right? It's not quite to 3 pi over 4. And this one looks like, it's kind of up on the high sides, but it's not pi over 4 because that's 45 degrees coming out. So it looks like theta is about pi over 3 on this one. And of course, I'm just basing that on what I can see from the angle back to the pole for both of these. I'm just taking a guess.